again, so I will. So I want to start here on my document camera, which I think you can see. Is it true?
Yep.
Yeah, so I just want to talk about some very, very basic things about the type of fuel cells we're going to be talking about. We're going to talk about what are called PEM fuel cells. That stands for polymer electrolyte membrane fuel cell. And these are very simple. You feed hydrogen from a storage tank to the negative electrode. You feed oxygen or air, presumably mostly air, into the cathode side. And the products are water, and of course, if you're feeding air, the nitrogen comes out as well as the other components of air. And the way the half reactions work is on the negative side, input hydrogen gets split on a catalyst, which is platinum, to protons and electrons. The electrons go through the outer circuit, and the hydrogen passes through the polymer electrolyte. And these protons and electrons combine with oxygen to make water. So it's an incredibly simple device, and it holds a lot of promise. So I want to talk about PEM fuel cells for probably 3 or 4 days. So now I'm going to switch to my PowerPoint. Where is it? Jeez. Here we go. Yeah. So here's one of the most available fuel cell cars, the Honda Clarity. You can't buy this car. You can lease it. And you can see the lease includes several unique benefits, including up to 15,000 of hydrogen fuel for the 3 lease term. This doesn't mean you get the $15,000 of hydrogen for free. It just means that you're insured to get $15,000 of hydrogen. And 21 days of complimentary Avis luxury car rentals. I think that's not because they expect the car to break down and you need to have service. It's because you may want to go away from the areas where there's a lot of hydrogen fueling stations at the moment. So if you look in this car, you'll find at the front end the fuel cell stack. I will talk about what a fuel cell stack is later on. There's a drive battery. I'm not sure what this is for. Maybe it's to provide extra power when you're going up a hill or accelerating. Fuel cells like to run sort of at steady state. So if you're continually asking them to deliver more power and less power in acceleration mode and deceleration mode, I think you would want a battery. And also the battery can capture regenerative braking, and the fuel cell cannot. And then you can see the hydrogen tanks, which are fairly large. These things store hydrogen at pressure somewhere around between 6,000 and 10,000 pounds per square inch. Just so that you know, the compressed cylinders that we use in the laboratory are compressed only to 2,500 pounds per square inch. These things are typically made of carbon composite so that the weight can be minimized. You know how heavy high pressure cylinders are that are made of steel. And because the pressures are so high, these things are always going to be cylindrical in shape with a spherical end or a complete sphere. There's no way that you can take the hydrogen tanks and put them under the floor of a car like you can with a lithium-ion battery pack that all the EV makers are now doing. All the battery packs fit under the floor pretty much. This thing has a 366-mile range rating, which is pretty darn good. It's very decent. Here's another one, the 2019 Hyundai Nexo. I like this. Hydrogen comes in, water goes in, water comes out. Here's some information about this Nexo. EPA range of 354 miles. It has three 10,000 PSI tanks that hold a total of 6.3 kilograms of hydrogen. So we'll do some calculations to figure out, you know, how much hydrogen it should take to go 100 kilometers. But you can pretty much do the math here. The hydrogen, you know, the thing about hydrogen is the molar weight is so low. 6.3 kilograms of hydrogen is a lot of moles, 6,300 moles of H. So that's why you can get such enormous range. The fuel cell stacks are somewhere around 200 pounds that you can see. So by the time you take the fuel cell stack and the hydrogen tanks and the drive battery, you know, it's probably fairly similar in weight to the lithium-ion battery pack in most EVs. It says it only contains 56 grams of the expensive platinum, whereas the Tucson needs 78 grams of platinum. And we'll learn later that the catalyst is where all the action happens in these fuel cells. I'm supposed to tell you a story about Mark Matthias here. So Mark Matthias ran the fuel cell program at General Motors for many years. And I remember sitting in a lecture that Mark was giving, and he said the fuel cells at that time contained way more platinum than this, probably more like 400 grams of platinum in a fuel cell stack that could power a car. And Mark said, listen, we have to get the amount of platinum in the fuel cell stack for a vehicle to be the same weight as the mass of gold in your wedding ring. And he took off his ring, he put it on the overhead projector, and he showed everyone, you know, that's how much platinum that you need to go for. And 56 grams are getting close. It's still more, I think, than the weight of a typical wedding ring. Platinum costs $48 a gram as of March 16, 2021. So that's about $2,500 per car just in platinum. And platinum is limited on the Earth. I don't know if there's enough platinum to make every car that everyone would drive a fuel cell powered car. But it's early days for fuel cell powered cars. Okay. This is a top-down view of a Toyota Mirai. It's again another vehicle that has, you can see a big hydrogen tank here under the rear seat. It has a drive battery. The fuel cell stack is up front. I think the electric motor's back here on the rear axle. Looks like another hydrogen tank stored back there too. You know, so these things seem to be adopting a more or less common design, with the stack up front, hydrogen tanks in the back, a drive battery, and a motor. Okay, any questions so far about the vehicles that we've been looking at?
I have a question about safety. Is that something that you're going to address in the lecture?
No, I am not going to address safety of hydrogen-powered fuel cell cars.
Okay.
Is there a reason why they all need multiple tanks? Is that just fitting with the geometry of the car?
I think it's just that the more hydrogen, the longer the range. So if you have a little extra space that you can't use for luggage or anything, why not stick a hydrogen tank there?
Okay, yeah. It just seems like having multiple tanks would increase the cost of the setup.
Well, these things are expensive as it is. You know, I think in the end, Scott, that it's okay. Say you just have the one tank and your range is 290 miles, okay? And then Elon Musk comes along and says, well, you know, with my Tesla Model Y, you can get 330 miles range. So then these fuel cell guys say, well, wait a second here. Let's just chuck in another tank and then we can beat the Tesla in range, right? And then you have that, you can say fuel cell cars have a longer range than electric vehicles do.
Okay.
Yeah, so I got interested in seeing where the hydrogen fueling stations were. So in Vancouver, these things that you see where my laser pointer is circling, these are hydrogen fueling stations. So there's quite a few in Vancouver, one in Victoria, and there's one over here in Kelowna. So in principle, you can drive your fuel cell powered car in this sort of region of British Columbia without any trouble. And you might wonder, why in British Columbia is there a relatively large concentration of hydrogen fueling stations? And it's because historically, Ballard Power Systems of Vancouver has been incredibly strong in fuel cell technology. You know, when I worked at Molly Energy from 85 until 1990, Ballard was just beginning their fuel cell work. And the two companies were literally the world leaders in rechargeable lithium and in fuel cell technology. And we would hire people from one another, you know, so we would steal from them and they would steal from us. And Ballard is still near the top of, you know, fuel cell technology. So they provided fuel cell stacks to cars and buses and all kinds of things over the years, and they're very, very skilled. And this is a map that shows where the hydrogen fueling stations are in California. So a lot in the LA area down to San Diego, San Francisco area, and then one in the middle, so you can go back and forth between San Francisco and LA without worry. And I don't know the current number for fuel cell vehicles on the road today, but last May there were 15,000 fuel cell vehicles on the road worldwide. And this is what a typical hydrogen fueling station looks like. Now, yeah.
Hey Jeff, I was just curious, like filling, is it the same as the conventional filling time? Just a couple of minutes, I guess?
Yes, it's about 5 minutes to fill. And you have to bear in mind that you're connecting a hose to your vehicle where hydrogen is going to be delivered ultimately at 10,000 psi. So I think, I've never used one of these things, but I imagine they're a little more sophisticated than just sticking a nozzle in a hole.
Makes sense, thanks.
Now I learned that Shell is big in promoting hydrogen fueling stations. And you would wonder, why is Shell involved in this? And then when you think about where does most hydrogen come from in the world today, hydrogen generally comes from steam reforming of methane because it's cheaper than making hydrogen by electrolysis of water. So hydrogen, in principle, should be a totally green fuel if you make it from electrolysis of water. But if you make it from, you know, from a fossil fuel and generate CO2 at the same time, that's not very intelligent. And that's the way most of the hydrogen produced today is made, is from fossil fuels.
Jeff, in these fueling stations, do we have the electrolyzer cells in there, or it is like transported to these stations?
Yeah, it's transported to these stations in a truck.
I see. Okay.
Or maybe in an underground pipeline, possibly. I don't know.
It is because of the cost of electrolyzer cells, I'm assuming.
Yeah, people don't make hydrogen primarily by electrolysis. They should be, but they're not. It's more expensive.
Okay, I see. Thanks.
Yeah, so this is something that has really influenced my way of thinking for many years. You know, if you admit and say, I'm only going to allow renewable sources of electricity from solar and wind, you know, that's it. Or maybe from hydro, or maybe even nuclear, no fossil fuels, okay? And then you're going to go and drive a fuel cell car. Well, you have to electrolyze water to make hydrogen. This is somewhere around 70% efficient, this process. And then you have to compress the hydrogen up to these high pressures. This is about 90% efficient. And then you have to run the fuel cell. And, you know, people talk about fuel cells being incredibly efficient. But when they say that, they're comparing them to internal combustion engines. A fuel cell operating near the peak power point is about 55% efficient. So when you multiply these together, it's 34% efficient in terms of going from the electricity produced by the renewable source to what reaches the electric motor in the EV. Whereas if you take a battery, the charger is about 95% efficient and the lithium-ion battery is about 95% efficient. So you get 90% efficiency. And what's the deal here? Well, it means you have to build 3 times as many windmills, or 3 times as many solar panels, or 3 times as many nuclear reactors to go by the lower path compared to the upper path. So if the lithium-ion battery is incredibly long-lived, you know, the upper path, I think, makes a lot of sense. And fuel cells also have a limited lifetime. We'll talk about why that comes about later on, too. Any questions about this slide? Okay, we'll move on. So we're going to talk now about polymer electrolyte membrane free fuel cells. And there's a book in our laboratory called Fuel Cell Systems Explained by Larmeny and Dix. And a lot of what I'll take from this section is taken from this book. So this book is kind of like Fuel Cells for Dummies, if you like. It's kind of the most basic book you could imagine. So it's a really good one to start with. So like the sketch I drew on my piece of paper at the beginning, this is a schematic of how a fuel cell works. Hydrogen fuel comes into the anode, which is porous carbon cloth with a catalyst layer deposited on the side that touches the polymer electrolyte membrane. So there's a catalyst layer deposited on this layer here where my laser's moving. And the cathode is virtually identical. It's another carbon fiber paper with catalyst deposited on the inner surface. The proton conducting membrane, or the polymer electrolyte membrane, is typically Nafion. We'll talk about what Nafion is later on in the section. So on this side, hydrogen is split into protons and electrons. The electrons go through to the load. They combine with oxygen from the air to make water. So it's really quite nice. So we see this half cell reaction. So the full reaction is just 2 hydrogens plus oxygen makes water. So we can work out delta G for that reaction, and then we can figure out the voltage. So it says describe the cell reaction on the board, work out the voltage. I did it over here on the right. So for this reaction, hydrogen plus oxygen goes to water. If it's going to water vapor at 80 degrees C, and that's typically what happens, the fuel cell is running hot. So the water that's produced is typically vapor at around 80 or 90 degrees C. That's about 54 kilocalories per mole for this reaction. And the voltage is minus delta G over NE. And you may not know, but 23 kilocalories per mole is 1 eV per atom. So with N over 2, you get 1.17 volts. Okay, so the open circuit voltage of a fuel cell should be around 1.17 volts. And it's kind of interesting, right? Because this is virtually equal to the electrochemical stability window of water, which is 1.23 volts. And if you think about what happens when water decomposes, well, it splits into hydrogen and oxygen. So it's virtually this reaction running in reverse. And if we had the product being water liquid at room temperature, then this would be very close to the value of the electrochemical stability window of water. So then here they just show what happens to the delta G if the product is liquid at 25 degrees C. You know, delta G is a little bit larger in magnitude than water vapor at 80 degrees C, right? So you get a slightly higher voltage if the product is water at 25 degrees. And then as the temperature goes up and up, the voltage of the fuel cell will drop. And a polymer electrolyte membrane fuel cell can only operate up to about 120 or 125 degrees C. And then beyond that, they just don't work well anymore. And the main reason is that the membrane has to have water in it to have decent proton conductivity. And if you heat the fuel cell much above 125 degrees C, the membrane just dries out and it loses all conducting properties. So these other temperatures would be used for considerations like high temperature fuel cells, solid oxide fuel cells, or whatever the case may be. Any questions about this slide? I have no idea if you people have had any exposure to fuel cells in the past or not, so I'm sort of starting from the beginning. Okay, so then we want to compare to the direct burning of the hydrogen and oxygen. Okay, so when you burn, the heat that you get is given by the change in enthalpy, not the change in free energy. So what they're doing here is they're comparing the delta G and the voltage, the maximum voltage that you can get, to what you would get, the high heating value efficiency limit, which would be directly burning hydrogen and oxygen and worrying about delta H. So the point of this is that if you directly burn it and you were able to, you know, capture all the energy efficiently, using the hydrogen in a fuel cell gives you 83% of the energy that you could get by direct burning. And this becomes worse as the temperature goes up because the voltage drops with the fuel cell and your comparison to direct burning gets worse and worse the higher the fuel cell operates. So at some point, you know, you may win by just burning the hydrogen and the oxygen. But there's a limit to how much energy you can extract by burning, and the limit is the Carnot limit. So if you have the cold reservoir of the heat engine at room temperature and the hot reservoir at excessively higher temperatures, this shows you the efficiency limit that you can reach for a heat engine. So a fuel cell is much better than a heat engine over most reasonable temperatures until finally around 700 degrees C, you'd be better off just burning the hydrogen in a heat engine and extracting energy that way, as opposed to using the fuel cell. So this is kind of off topic to some degree, but you know, sometimes people say fuel cells always have a higher efficiency than heat engines, but at super high temperature they don't. All right, so now let's talk about the major components of a polymer electrolyte membrane fuel cell. So we're going to go in detail and look at all the different parts of a fuel cell now. All right, so what you would typically have in a fuel cell stack is a set of repeating units. So you have something called a membrane electrode assembly, and it says describe the membrane electrode assembly on the board. I have a slide coming next that will describe the membrane electrode assembly on the board. So we'll call this MEA, membrane electrode assembly, because it consists of the proton electrode the polymer electrolyte membrane, and the positive electrode and the negative electrode that have been heat laminated on either side. And then it's constrained in this little holding frame that you can see. And then what you have is a gas flow field plate, because you have to be able to distribute the hydrogen uniformly, or as uniformly as possible, over the whole surface of the negative electrode, which would be, say, on the left of this MEA. And then similarly, you have to have a flow field plate on the air side to distribute the oxygen in the air uniformly over the positive electrode side. So that's what these things are. They're called bipolar plates. In the beginning, these were made out of graphite, and they were machined. These little channels that you would see were machined by a machinist. And then ultimately they were machined by a computer numeric controlled machine, so automatic machining. And then eventually, because that was way too expensive for mass production, these started to become made by using a resin. And then, as we learned in our section of the course on soft carbons, you pyrolyze this thing in inert gas. So you take this thing, it's pressed, graphite powder pressed in a resin, and then that's heated to high temperature to decompose the resin and kind of glue this thing together. So you're able to press in a mold these channels and then heat this thing up to high temperature. So it's kind of like making an object out of clay and putting it in the kiln, and it comes out hard and conducting and the way you want it to be. All right, so then these repeating units are just stacked one after the other, and each one gives you, the order of a volt. So 1 volt, 2 volt, 3 volts. So here you get 3 volts from this stack that you see. And distributing the hydrogen and the oxygen, so that they go, if the first stack uses all the hydrogen and there's none left for the other cells in the stack, that's bad. So you have to be able to distribute the hydrogen uniformly amongst all the cells in this series stack, and the same for the water, same for the oxygen, sorry. Okay, so let me show you what a membrane electrode assembly is all about, and then we'll answer questions about the fuel cell stack, okay? All right, so this is an MEA. It has a bunch of different components in it. We'll start in the middle. This is the proton conducting membrane. And like I said, it's made of Nafion, which we'll learn about later on. And it can conduct protons. Then there's a catalyst layer that's usually applied to the surface of the gas diffusion layer prior to the lamination of the gas diffusion layer to the proton conducting membrane. So this layer would be about 15 microns thick. So where my laser is going back and forth, maybe 10 or 15 microns thick. And it consists of carbon black, which we know what carbon black is. And on the surface of that carbon black has been deposited nanometer sized platinum catalyst particles. So these might be somewhere in the range between 20 and 100 nanometers in diameter, these little platinum grains on the carbon black. And then you can see this gray stuff in amongst the catalyst layer. And what that is it's Nafion that has been made into a slurry. So you would make, to coat this anode catalyst layer, it's a lot like coating a battery electrode the way we do in our lab or in the Overback lab, where you make a slurry of the active materials and a binder in a solution. So here you would use the catalyst the platinum on the carbon black, then you would dissolve some Nafion ionomer in a solvent. I think it's isopropyl alcohol, I can't remember. And then you coat that out on the surface of the gas diffusion layer. And you end up with this little Nafion channels in here. And the reason that this is here is because you have to be able to get protons from the carbon supported catalyst here through these Nafion fibrils into the proton conducting membrane and then over to the other side, right? And then this gas diffusion layer is just a carbon fiber paper. So I don't know if any of you have ever thought about carbon fiber paper, what it is. Maybe you've seen it, maybe you haven't. But I'll tell you how you can make it yourself. Take a piece of your shirt and stick it in the tube furnace under argon at 1,000 degrees C. And it'll come out all the hydrogen and oxygen and so on in the cotton or polyester or nylon or whatever it is in your shirt will pyrolyze away, and you'll only be left with the carbon, and they'll retain their fibril shape just like the thread used to weave your shirt, and you will get carbon fiber paper. Okay, so that's the simplest way to make carbon fiber paper, is just pyrolyze your shirt. So the positive side is exactly the same as the negative side. Sometimes it's of benefit to use different catalysts at the positive than the negative, but they're always platinum based. The anode side is always pure platinum, and the cathode side might be a platinum alloy, something like platinum nickel or platinum cobalt or something like that. Okay, so let's have questions here about this MEA and the fuel cell stack, if there are any.
Jeff?
Yeah.
I thought people started using other catalysts besides platinum, like carbon-based catalysts as well, or is it still only platinum?
There's a huge amount of research going on non-noble metal catalysts. So like Ahmed mentions, things like carbon nitrogen, carbon iron nitrogen, things like this. But first of all, their catalytic efficiencies are way less than platinum, and their lifetimes are very, very poor at the moment. So they have not been commercialized yet and may never be. So, you know, we worked, okay, so let's talk about my experience with fuel cells. So I think from about 2001 to, I don't know, 2000, whenever Tim Crouch left the lab, maybe that was 2014 or 15, we had a fuel cell project with 3M on exactly this design, a polymer electrolyte membrane fuel cell. So we worked a lot on catalyst optimization, alloy catalysts, platinum nickel, platinum cobalt, platinum ruthenium, platinum anything, pretty much, even platinum silicon dioxide, for Pete's sake. And we also had a program on non-noble metal catalysts. So we made them by sputtering, by solution-based methods, all kinds of things. So I know something about fuel cells, so it's not like redox flow batteries where I don't know anything. Okay, more questions.
The bipolar plates then act as current collectors, right?
Yeah, the bipolar plates act as current collectors and also as the gas transporter to get the gas in and the water vapor out through those flow channels.
What is it with platinum that makes it such a efficient material for this application?
Well, what is it that makes platinum the best catalyst in the world for just about anything? You know, that drove us crazy for years. Why is platinum so good, and why don't other things work as well? You know, for the negative side, palladium works about as well as platinum, but for the positive side, nothing works as well as platinum. And all the alloy strategies really turned out to be more or less diluting down the amount of platinum that you would need. There are theorists like Jens Norskov who have written very nice papers that explain, you know, why platinum is the best, and it has to do with reasons that are beyond the scope of this class and beyond the scope of me trying to explain with a voice and not, you know, a lot of diagrams. But suffice it to say, platinum is the winner by far.
Would a very vague, simplistic answer be that because it's unique electronic structure compared to other elements?
Yeah, it's a unique electronic structure. Also, it's a noble metal. So that means that its surface is generally platinum metal. And that's not always the case when the fuel cell voltage becomes large. The surface gets covered with platinum hydroxide and platinum oxide, which then limits its activity. So when the fuel cell voltage then goes down again below about 0.8 volts, all those species are stripped off the surface, and then the catalyst reaches its full activity. So it has to be noble, and its electronic structure has to be right. Okay, so let's move along. Yeah, so this is, you know, this is a picture of one of these flow plates here. So this is just to tell you that, you know, these contain 85% powdered carbon, molded by SGL Carbon, the world's largest producer of carbon and graphite products. With a cycle time of just 30 seconds, these plates can be produced in volume without the labor, cost-intensive machining and other finishing steps needed to form their intricate channels when other materials are used. Okay, so this is, flow plates are made by this pressing and heating method, not machining graphite. Yeah, so I would normally pass around a gas diffusion layer, but it's hard because we're not together. But this is what they look like. It's really just carbon fibers woven together. This is a 200 micron scale bar here. So you can get a feeling for the size of the holes in the paper. Normally made from polyacrylonitrile cloth, which is pyrolyzed in inert gas to turn into carbon. And then one side is coated with water repellent. I don't know why it says, oh yeah, conductive layer, the Teflon and carbon black. So it's really important that you can remove water from this space. Imagine on the positive side where you're creating water. And imagine if this space floods. So flooding in fuel cells is a jargon that means the cathode side, all this pore space is full of product water that's not taken away fast enough. So once it floods, then you can't get oxygen to the catalyst anymore. So if you think about the structure of this MEA, this is creating water, and the water has to get out for more oxygen to get in. So if this whole gas diffusion layer fills with water and floods, then the fuel cell shuts down. You can't draw any current from it. So you try to get the water out of here by making this, what did they call it? Microporous layer to repel water. This is a picture of a gas diffusion layer. They're made on giant rolls like this. So this is, I don't know, this is probably half a kilometer or a kilometer of gas diffusion layer, and this would be 3 or 4 feet wide. This was made at Ballard in Vancouver. So it has a carbon fiber paper, a Teflon treatment, and a microporous layer coating. So even though these things are made at scale. And it's important to talk about the properties of the gas diffusion layer. So let's take a look at some Ballard products. So here's the thickness, about 200 microns up to 275 microns, so different types of thicknesses. What's the weight in grams per meter squared? So they're really light because they're very, very porous. So 80 grams per meter squared, 98 grams per meter squared, whatever. And here they tell you the bulk density in grams per centimeter cube. Remember, these are made of carbon, which has a density of 2.2 grams per centimeter cube. So these are about, you know, a little more than a tenth the density of graphite. So these are like 85% porous, these things. Okay. And then they tell you what the through plane resistivity is. So that's the resistivity perpendicular, you know, through the thickness of this thing. So it's very thin, but this is the resistivity. And I'm going to talk on the next slide why this is important in a fuel cell. You really want to try to minimize electrical resistance everywhere you possibly can in the fuel cell situation, because the current densities are massive. So who cares about the through plane resistivity of 14 milliohms per centimeter squared? 14 milliohms per centimeter squared. Fuel cell current densities are the order of an amp per centimeter squared. In fact, good fuel cells today run more like 2 amps per centimeter squared. And if you compare that to lithium ion, you know, a C rate in lithium ion is about 5 milliamps per centimeter squared. So this is just 200 times bigger, massive, huge. And then when the current densities are this massive, you really have to worry about every little bit of electrical resistance you have. So what's the voltage drop per fuel cell? You have 2 gas diffusion layers, one on the anode side and one on the cathode side. So you got 2 layers, 1 amp per centimeter squared times 14 milliohms per centimeter squared gives you 28 millivolts. Okay. So out of a fuel cell open circuit voltage of around 1 volt, this is pretty small. And this is pretty small compared to the other losses that take place in a fuel cell, as we'll see going forward. Any questions about that? All right, so let's talk about the catalyst. So usually it's platinum, and always on the negative side it's platinum. More modern catalysts could be platinum alloy catalysts, and we'll talk more about that later. So this is what a TEM image of carbon black might look like, you know, a 10 nanometer scale bar. So you have these little sort of spherical balls of carbon that are connected together. They're sort of like a pearl necklace. In fact, there's one carbon black that's actually called black pearls. And we used it a lot in our fuel cell work. It was called Black Pearls 2000 because its specific surface area was 2,000 meters squared per gram. And they looked like little balls, you know, in like a pearl necklace. So it's kind of cool. And then here is a carbon black that's been decorated with platinum nanoparticles. So all these dark things that you see here are platinum nanoparticles, and these are a few nanometers in size here. Now normally that's a much higher catalyst loading than you would see in a fuel cell. You know, the weight percentage of platinum here is quite large because platinum is very dense compared to carbon. So typically you wouldn't see this much platinum on a catalyst. Okay, so let's talk more about the platinum catalyst here. So we've got four curves on this graph. Two of them describe the specific surface area, and two of them describe the crystallite size of the platinum based on X-ray diffraction using the Scherer formula. So the Scherer formula allows you to figure out the crystallite size based on the width of the X-ray diffraction peak. So let's take a look. So the specific surface area of platinum per gram of catalyst, so about 70 for this one, and about 140 for this one. And as the platinum loading goes up, the specific surface area goes down. So you're thinking, why does this happen? And then you learn at the same time, the blue squares correspond to this color that could be green. At the same time as you're increasing the loading, the size of the nanoparticles gets bigger. So the surface area to volume ratio gets smaller as the size of the loading goes up. So it would be your intent to increase the loading, but not increase the crystallite size to maintain, you know, a high surface area per gram. So the way that these catalysts are applied, usually in a solution-based precipitation process, leads to this interaction between loading and crystallite size. Okay. And the same is true for the other carbon. As you increase the loading, the surface area drops and the crystallite size goes up. So I'll just do one more slide, I think. Yeah. So the question is, do these surface areas make sense? So it's important to know how the surface area per gram varies for spheres. So I'm going to switch to my document camera. You just derived this formula. It only takes a second. Do you see my document camera now?
Yep, we do.
Yes.
Okay, so specific surface area of surface area of a sphere is 4 pi r squared. And the mass of a sphere is the density times the volume, 4/3 pi r cubed. So if you want The specific surface area, that's the surface area over the mass. That'll come out in meters squared per gram. It's 4 pi r squared over rho times 4/3 pi r cubed. And that turns out to be, the 4's cancel, the pi's cancel, a bunch of the r's cancel. It's just 3 over rho r. And that would be the BET surface area. So now we go back, we take a look at our graph. So this is the density of platinum here. It's really dense. And I've just taken that little formula and calculated what the specific surface area should be based on the crystallite size. For
Hey, Jeff,
spheres.
can
Yeah.
we go back to your slides?
Yeah. Sorry, I didn't make the change. Let me find it. What do you see now?
Your document camera.
Okay, cool. What do you see now?
I see your desktop. Yep, there you go.
Okay, great. Yeah, so here we are. We have a graph of specific surface area versus crystallite size just from that very simple formula. 3 divided by the density divided by the radius, right? So here we are. And then you can just say, okay, what happens here? I think this is diameter, actually, what we're talking about here on the horizontal axis. So, you know, if you have a 150 meters squared per gram, the size should be about 2. If you have 100 meters squared per gram, the size should be about 3. So if you have 150 meters squared per gram here, the size is about 3, right? If you have 100 meters squared per gram, the size is a little bit under 3. Over here, if you have 60 meters squared per gram, this green circle, the size is up around 5, 4.5. So let's check that out. If you have 60, size should be 4.5, right? So there's no mystery about why the specific surface area changes with the size of the platinum particles. The really annoying thing is the fact that as you put on more loading by these co-precipitation methods, that the size of the particles gets bigger. So you're loading more platinum, which costs money, but you're not winning based on total surface area. Okay, this is a good place to stop. Is there any questions at this point?
I'm not familiar with the co-precipitation method for this synthesis, but would it be possible to synthesize small 2 nanometer sized platinums nanoparticles separately and then attach them to the carbon black somehow? That way you can keep the low particle size and increase the loading? Or is that too costly compared to a co-precipitation?
Yeah, I'm not sure how easy or difficult that would be, how to attach it well and disperse it well. You know, 2 nanometers is pretty tiny, and they might tend to agglomerate while you're trying to put them on there. I think the way this is mainly done is you take something like chloroplatinic acid, and then you react that with a base, and you can precipitate the platinum somehow. But remember how it's done, really. We will see later on in this course that you can sputter deposit catalysts onto suitable supports, and that way, you know, create pretty small nanoparticles as well.
I see. Yeah. Thank you.
Okay, any more questions? We're at a good spot to stop based on where we are in the lecture. Okay, hearing no more questions, I'll say goodbye.